Hey, Year 12s. Good to see you guys. Thanks for coming. Hope you're all okay and you had a nice long weekend. I'm just waiting for the video to start on my YouTube channel. I'm just using the two computers. There we go. Quite a big delay, really. About a minute. Just going to check the sound. I'm just waiting. There you go. Sounds good. I like it. I'm just going to turn down the quality of my video so that it doesn't affect my bandwidth. There we go. Not that it should. Cool. So we're doing well on the reg. Haven't got Adam yet. Still no Adam or Angel. There's Ansh. There's Ansh. I like it. Aisha? Not yet. Alistair? Yes. Good to see Alistair. Isha? No. Emmeline? No. Hermione? Yeah. Meryl? Yeah. Manisha? Yeah. There's Emmeline. Amazing. Manisha? Yes. And then Minwee? Yeah. Got her as well, which is great. Misha? Oh, there's Isha. I like it. There's Misha. No murder yet. Got Julian. Got Oliver. Amazing. Doing really well. Got Isha. Isha's just signed in. Amazing. So just missing Adam, Angel, Aisha, and Murdo. That's all. There's Murdo. I like it. And there's, yeah, perfect. There's Murdo. Love it. How's it going, guys? Just missing 3 people, Adam, Angel, and Aisha. Giggity. G'day, g'day. I like it. Wow, very Australian there, Murdo. So what do you mean I'm here? Oh, I'm just saying that you're here for registration, that's all. Funny. Right, guys, today we're going to be looking at moles and gases today, which is quite exciting. I'm all set up to go through I gave you an additional homework on Avogadro's constant and this whole idea of counting particles and using it. Tried my best. Oh, there's Aisha. I did my best to try and find a decent selection of them. Happy to put another set together if people want it. Just missing Angel and Adam now. I think what I'm going to do is I'm 3 minutes in. I'm 3 minutes in, so I think I'll start the lesson. If someone could do me a favor and send Adam and Angel a message, that would be super handy. I'll mark them as missing for the time being, and then mark them in when they arrive. I like it. Okay, right. Let's crack on with moles and gases in our homework review. Right. Let's share screen. My laptop's gone through an update today, so I'm kind of hoping it's going to be a bit better today. Okay, right. You guys should be able to see my screen now. Let's see how we can get on. Okay, right. So the homework is just really designed to get you guys to start contemplating the kind of, these are all A-level questions. And so really nice to see how they use these different units that we mentioned in the previous webinar and putting these into application. I am very, very aware that when you teach A-level, there is a huge, huge translation issue, which is the students often leave my lessons thinking, yeah, on it, absolutely solid understanding of what's going on. And then they see the exam questions and they are very, very much shocked by the difference between what's taught in lesson and the ability to apply that understanding. And so I have created the Year 12 support sheet. I'll give you guys all access to that. When I feel like when you guys are ready, I don't want to give you guys access to something that you then won't be able to do the questions of, because it's rather disheartening if you can't. But I'll give you that soon when we come to the end of our topic of calculations. We're about halfway through, I reckon. Maybe not quite halfway through, but nearly. I know that this is one of the things I'm going to quickly mention, is that I'm very aware that this whole lockdown situation and these online lessons that you guys are getting for this introduction to Year 12 is going to end soon. I'm not going to end them. I want to finish off calculations as a unit, And I feel like there's huge value in that for anybody who's staying or going from BSKL. So I would have to take the register, and you can watch it back at your delight at any time. But I do think it's worthwhile sticking with this and finishing the topic. And then you guys can then start the process of doing the translation using my support booklet. So, okay, let's go back to this. Okay, so what is the number of atoms? I need my calculator on standby. What is the number of atoms? Now that's the key, isn't it? That there is the trap. Yeah, it'd be quite nice to do this in red since I'm marking it. Yeah, the trap here is the atoms. Yeah, because we realize what we're going to be doing is if we've got moles of ammonia, yeah, then the problem is that doesn't really work for atoms. That's the number of molecules of ammonia. So in order to then translate this over to atoms, we need to multiply that number by 4. Yeah, and the reason being, of course, is because each ammonia molecule contains 4 atoms. So I'm actually going to have 0.04 moles of atoms. Yeah, just to quickly show you why this is because if I take ammonia and I separate it into its individual atoms, yeah, that's what it would look like. Yeah, this equation does appear every now and again. Yeah, this is bond enthalpy calculations where this equation matters. But we're going from a ratio of 1 molecule, and I'll put the one molecule. Yeah, 1 molecule. And if we split it up, we would get a total of 4 atoms. I hope that makes sense. Yeah, so now that we've got the moles of atoms, yeah, we can now multiply that by Avogadro's constant, and we're going to get our answer. So calculator, 0.04 multiplied by 6.022, exponential 23, and I get 2.4 times 10 to the 22, 2.41 if it's rounded to 3 sig fig. And so there's my answer. I like it. Okay, nice, relatively easy start, I think. Oh, Adam has sent me a message. I think it's because I'm on a phone. I'll try and get on my Mac. Okay, I can't chat to say I'm there. Oh, thanks for letting me know, Adam. I do appreciate that. I'll mark you as in. That's great. Thanks for letting me know. Really appreciate it. Okay, next. This one's a clever question, this, because they've done a sneaky trap. Yeah, we've got 1.41 kilos of trifluoroethane. Yeah, calculate the number of molecules in 111 trifluoroethane in the refrigerant. Give your answer to the appropriate significant figure. Now, that's really clever because the thing is, you see, Avogadro's constant, yeah, this number here is being given to 4 sig fig. Yeah, but then the kilos is given to 3 sig fig. So we have to use the lowest significant figure in the question. You can't give a number beyond the lowest accuracy in the question. So the answer must be to 3 sig fig. It's a clever little trap, that. It's really clever. So, okay, so what we've got, the first thing we're going to have to do is we realize that the number of moles is grams over rams. We need to get to moles. Well, the kilos therefore needs to be translated. So we need to multiply that by 1,000 to convert it to grams. Yeah, and there's my grams. Now what we can do is we can now run that number, of course, into grams over rams. Yeah, there's my rams. I'll color code this. Yeah, there's my grams is there. Yeah, what we now need to do, of course, is work out the rams. But it's given us the formula, which is nice. CF3CH3. So to work out the rams, we're going to have carbon, which is 12.0. But I've got 2 of them, so times that by 2. I'm going to add that to fluorine, which is 19.0, times by 3. And then we're going to add that to hydrogen, which is 1.0, times by 3 as well. Total number. And of course, there's a trap in here as well, isn't there? Yeah, so because the problem is, because they're all 0.0s, the 0 on the calculator is going to disappear, and that's the trap. Yeah, so 12.0 times 2 plus 19.0 times by 3 plus 3 as well. So the number there, which is the trap, we can now apply all of these. Yeah, and our number there is 84.0. Without that 0, you would have lost the second mark. Do watch out at A level. Now we can insert all of our numbers. 1,410 grams over 84.0, and I'm going to get 1410 divided by 84 gives me 16. So I've got 16.8 moles. Now here's a second trap here, folks. That is it to 3 significant figures, but I've got to keep that number on my calculator. In reality, I've got 16.78571429. Yeah, I've got the real thing. Just going to erase this and keep 84.0. Yeah, there's 84.0. And now I'm going to multiply that number by Avogadro's constant. Yeah, and I'm just going to remember to round the answer to 3 sig figs. So I'm using the number on my calculator, not my written down number, multiplied by 6.022. Exponential 23. I can still use that number. My final answer will be equals 1.01 times 10 to the 25. And there's my answer. So that answer there, folks. Yeah, there's your, and then 1 mark for 84.0. That question's really interesting because it should be a 3 marker. Yeah, and it's a typical Edexcel thing. They obviously overran. If you've not had me before as a teacher, you won't recognize that I often harp on about the idea that when they create their papers in Edexcel, they write the paper and then they count up the marks. They've got to hit all the topics, and they often overshoot. So then what they'll do is they'll make some of the 3 markers down to 2 markers. So this usually should have been a 3-mark question, but it was reduced to a 2. Because usually you'd have to do the conversion to grams. But anyway, let's continue. Right. In an airbag, sodium azide, ooh, it's a rather powerful explosive sodium azide, decomposes to form sodium metal and nitrogen gas. The sodium metal then reacts with potassium nitrate to produce more nitrogen gas. If 2 moles of sodium azide react in this way, how many molecules of N2 will be formed? Now, can I just say that this question here is a bit mean. We haven't done reacting masses yet. That you guys, I'm hoping, are going to have been able to use your reacting mass knowledge from GCSE to answer this question, because it's a rather clever trick, this one. So what you have to do is you have to insert, we've got 2 moles. We've got 2 moles of sodium azide going in from the question. Yeah, now that sodium azide is going to produce 3 moles. Yeah, we know from the equation that that's going to make 3 moles of nitrogen. Yeah, and I'll put that down here. 3 moles from equation 1. Yeah. Now the next thing is that is also then going to make 2 moles of sodium metal. Now that sodium metal is going to drop down into the second reaction. So I'm going to get 2 moles of sodium, and then that is going to react again, but it's going to react in a 10-to-1 ratio. Yeah, the ratio from the equation is 10-to-1. So what that means is I'm going to have to take this to go from 10-to-1. Yeah, the ratio is 10-to-1. I'm going to divide that by 10. So I'm also going to produce 0.2 moles of nitrogen in the second equation, because the 2 moles of sodium that was created in the first reaction then reacts with the potassium nitrate to generate more. So I'm going to have to add to that 0.2 moles. So the total moles of nitrogen gas in total, of course, is 3.2. It's a clever trick, that, and that's going to be N2. Right, so now we've got the N2 moles, we can now use Avogadro's constant, multiply that 6.022 times 10 to the 23. So I'm going to do 3.2 times by 6.022 exponential 23, and I get 1.93 times 10 to the 24. 1.9, there it is. Tick, and I'm done. That, by the way, that really was beyond, that was a hard question, that, folks, because you guys haven't really looked at this idea of multiple equations before and how you move the moles around. So that question there was a challenge question for you guys. Can I have a quick shout out on the chat, please? How many people got the correct answer? Be really nice to give you guys a bit of props for that, because that was a really hard question. That's very much A-level. Right, next one. Use the information to answer the question below. A saturated solution of magnesium hydroxide contains 0.116. Oh, well done, Oliver. Great job. contains of grams in 10 liters of water. In this solution, the magnesium hydroxide is fully dissociated into ions. Which of the following is the concentration of the Mg2 plus ion in the saturated solution? So, okay, so clever question. Now, you guys, this has got a whole load of GCSE stuff in it here, guys, that you guys will have to be recalling. So the first thing is the idea that we've got magnesium hydroxide, yeah, MgOH2, and when it goes into water, it forms Mg2 plus ions and 2 OH minuses. And these are aqueous. There's the dissociation equation. It's the dissolving one, really. Yeah, so that's now dissolved. Now, what we realize is the ratio between the magnesium hydroxide and the magnesium ions is a 1-to-1. This is very much another reacting mass. I apologize. But we've talked about ionic equations, and you guys would have been able to access this to a certain extent. The next thing is a saturated solution. Contains this many grams in a 10-liter solution. Now, what they're wanting you to do is, which of the following is the concentration? Now, they're in moles per dm cubed in all of our answers. So what that means is, if this is the concentration in 10 liters, yeah, grams per 10 liters, well, what we would immediately recognize is that 0.1166 is grams per 10 dm cubed. You can't do that anymore. Per 10 dm cubed. Well, what would be the grams per 1 liter cubed? Let's convert to dm first. So I'm actually going to have 1/10 of the grams in that volume, aren't I? So I'm going to have 0.01166 grams per dm cubed. So that's the first conversion. This is the mass in 10 liters. Well, what mass would I have in 1 liter? I would have 1/10 of that mass. So we've done that conversion. Now what we need, now that we've got to dm cubed, we're halfway there. We've ticked that column. Yeah, now we need to get to moles per dm cubed. Well, this is the grams of magnesium hydroxide. Now that's quite clever, that, because what I want to now do is grams over rams. Yeah, so number of moles equals grams over rams, which is 0.0166. Oh, I've missed a 1 there. 1166 grams, and I've got that, and that's magnesium hydroxide. So I need to work out the MR of that guy. Now, magnesium is a tricky one, 24.3 on the A-level periodic table. And there's one of those plus oxygen, which is 16.0 times by 2, yeah, plus hydrogen 1.0 times by 2 as well. So let's add that up, 24.3 plus 16.0 plus 16.0 plus 1 plus 1.0. So we've got an answer there of 58.3. So I can work out the moles of magnesium hydroxide in that 1 liter. 0.01166 over 58.3. So I get an answer of the number of moles of magnesium hydroxide of 2 times 10 to the minus 4 moles. I'm actually going to write down moles of MgOH2. Yeah. Now, the great thing is the dissociation we've already discussed is a 1-to-1. What that means is I therefore have 2 times 10 to the minus 4 moles of magnesium ions in solution, Mg2 plus aqueous, because the equation was a 1-to-1. Again, very much a reacting mass style question. Now what we need to do is now that we've got moles, we've already done it. That, of course, we can put that in as moles per grams per dm cubed at the beginning. And so the answer is 2 times 10 to the minus 4. And the answer, therefore, is D. Clever question. Really hard. That there is just the last 2 questions. Now, that's really challenging. Yeah? Okay, let's go to the next one. These are much harder than the previous ones. I do apologize. But the thing is, guys, these are all A-level questions. Yeah, and so it is just a case of you've got to practice them. That you get used to it after a while, I promise. The more you do them, the easier they get. So we've got balance the equation. That's quite nice. So they've got a nice balance. So 3 magnesiums, 2 nitrogens, 2 nitrogens. Hydrogens, I've got 2 on this side, but this one I've got 2 here. So 6 plus another 6 is 12. So I need to have 12 over here. So I'm going to put 6 there. And now we can check our oxygens. Yeah, so we've got 2 there, multiplied by 3, I've got 6. So that now adds up. There's the first mark for this bit. Right, now that we've balanced the equation, calculate the number of moles and hence the number of molecules of ammonia in 0.263 grams of ammonia. Right, okay, so the number of moles and hence the number of molecules. Okay, so, oh, that's interesting. They've got nothing, the equation is completely independent. It's a completely independent question. So even if you haven't balanced it correctly, you can still access the next one. So calculate the number of moles and hence the number of atoms of ammonia. So number of moles is grams over rams. We know this, we're using this a lot now. Yeah, so number of moles is grams 0.263 over, and that is the grams of ammonia gas. So we've got the MR of this, of course, which is 14.0 plus hydrogen 1.0 times by 3. So the answer is 17.0. So there's the third mark. Yeah, so we've got, so far, we've got a mark for that guy, a mark for the balancing of the equation. Now that we can work out the moles, 0.263 divided by 17.0. Lose that mark if you've forgotten to add the 0 in. So the moles equals 0.0155 to 3 sig fig. And I'll put moles, mole. So there's the second, there's a third mark. Now we need to get to Avogadro's constant. We're going to take that number and I'm going to use the one on my calculator. Yeah, so I'm now going to take that and multiply it. So 0.0155 multiplied by 6.02. Notice they've changed the significant figures on Avogadro's constant. You must always use the one that they give you. I'm not using this number in reality. I'm using the number on my calculator, 0.015470588, multiplied by 6.02 exponential 23. There you go. And the final answer is 9.31 times 10 to the 21 molecules. And it is molecules in this case, so we don't have to multiply for the atoms, which is great. Tick it if you got it, guys. 4 marks in total. What a lovely question that is. Right, next, calculate the mass in grams of a single atom of this isotope of sodium. Oh, that's, oh dear. Oh, hang on. That's weird. It is part 3. It's, guys, I'm very sorry. You have to have made a massive assumption here. That question's been taken from another one. Yeah, we're going to have to, so that's interesting. They gave us another isotope. But no, not to worry. We have to make an assumption. Sodium is element number 11, mass of 23. So with this question, you guys are gonna have to make a massive assumption that we're gonna use the common isotope from the periodic table, which is number 23. So, and this is really clever. This question actually I need to reinforce. This one's important. This comes up a lot at Edexcel. I was quite surprised when I saw it. And the way that you have to do that is, we actually know a fact. 1 mole of anything is its AR or MR in grams. So 1 mole of sodium 23 is equal to 23 grams. That's a massive leap of faith that you guys, number one, you guys have to have made an assumption that we're going to use the most common isotope. Yeah, and the second thing is recognizing that 1 mole of anything is its AR in grams. So I've got 23 grams of sodium will be equal to this many particles. So if I now divide 23 by Avogadro's constant, and notice they've given a different number. Isn't that fascinating? You've got to use the number that they give you. 23 divided by 6.023 exponential 23. So the mass of 1 atom of a most common isotope of sodium is 3.82 times 10 to the minus 23 grams. Very tiny. That makes sense. A tiny mass for an atom. Yeah, that's a really big leap of faith, that, guys. I just want to explain that. Yeah, this sentence here. Yeah, 1 mole of anything is its AR in grams. Yeah, so if we have 1 mole of anything, yeah, if we have 1 mole of anything, 1 mole of sodium, yeah, which would be 23 grams. If you were to count all the atoms, we know that I would have Avogadro's constant there. In this case, I don't know why they use the 3, but whatever. They're doing it so people it's a trap to try and why exponential and not to the power? Exponentials on my calculator, Emmeline. EXP for me. Yeah, you can say to the power, I think isn't, EXP, sorry, I shouldn't say exponential, I guess. I take like 10 seconds to think about what it means every time. Sorry, it's just on my calculator as EXP. Yeah, meaning power. Sorry about that, my bad. I'll say to the power if you like. Oh, I can adapt. So if we've got 23 grams containing this, well, if I just divide the grams by the number, I'm going to get the mass of a single atom. Anyway, next question. Oh, I quite like this one. A brand of fluoride tablet. Ugh. Okay. Recommended by dentists to strengthen enamel on teeth contains. So each tablet contains 2.2 times 10 to the minus 3. Oh, no units. Guys, they've made a mistake there. Yeah, that's really stupid. There's no units, but this is a real question from a paper. 10 to the minus 3 sodium fluorides. I'm assuming that's going to be moles. I have to make a massive assumption again. The total mass of the total mass of fluoride present in 100 tablets is, right, well, hang on a minute. That there is sodium fluoride. Well, oh, hang on a minute. Look at the question. That's interesting. Yeah, because they're doing grams. Percentage composition. Isn't that clever? That's really hard, that. Just, I don't mind. Just small. Don't be silly, Emily. So hang on a sec. If we wanted to work out if that's sodium fluoride, what we need to do is we need to separate sodium fluoride. What's the percentage? Right, we're going to multiply it by the percentage. And the percentage, of course, is sodium fluoride, NaF, is 23.0 plus 19.0. Total number, 23 plus 19 is 42. Right, oh, that's interesting. How fascinating. So that's 42. So 19 over 42 would be the quantity of fluorine in it. Yeah, we're doing times by its percentage over 42. We've got to do that. That means there's only one answer, and that's A. And that clever, times by 100, that makes sense. So A is the answer, because we've got, whatever it was, if this was grams, it makes no difference. We still need to find the percentage of fluoride rather than the sodium fluoride. So we have to do this as the fraction, as the percentage. If some people don't like doing that, if you did 19 over 42, you're going to get the percentage of fluorine, which is 0.452%. Yeah, well, it's not a percentage because I haven't times it by 100, but that's the fraction. That's the value instead of the fraction. So anyway, but then of course, the equation is written out for you. So it's 19 over 42 times 100. That's really clever, that. Doesn't actually matter that they've given us no units. Very clever indeed. Very tough. Next, the drink driving offence is committed with a blood alcohol level of 80 milligrams per 100 centimeters cubed of blood. What is the concentration of ethanol if there are 80 milligrams? I gave you this one before. So the first thing, we need to get to moles per dm cubed. And at the moment, we have 80 milligrams per 100 centimeters to the minus 3, because it's per. That's how we get the per. Right. First bit, if I need to get per liter, first thing I'm going to do is I want to get this to dm cubed. How do I get 100 centimeters cubed to dm cubed? I times it by 10. That's going to give me 800 milligrams per liter. Now I need to get out of milligrams and into grams. So I need to now, I'm just going to divide that by 1,000, yeah, to get it into grams. Milligrams is tiny. So I only end up 0.8 grams per, can't do that now at A level, per dm cubed. Now what I need to do is get to moles. Number of moles equals grams over rams. It doesn't matter that the dm's there, it's not going to change anymore. So now we need to work out the MR of ethanol, which is 46.0. Reorganize my equation, times both sides by rams. Yeah, it's going to give me, hang on a minute, I want moles. That's already done for me. Lol, such a habit. So 0.8 over 46.0, which is the MR of ethanol. If anybody's wondering how I know that, you're meant to know ethanol as this, and then you can work out its MR. Carbon 12.0 times by 2, plus hydrogen 1.0 times by 6. plus oxygen at 16.0 times by 1, and you get 46.0. It's a useful MR to know that one. So if I just do 0.8 divided by 46, I get 0.0174. In reality, the answer is B. Clever question. Next, I thought I'd give you that one as a repeat, to see if you guys could still access it, having done it in the lesson last time. Okay, the mass of 1 mole of hydrogen atoms is, okay, that's interesting. And that of one H1 atom is this in grams. Use this data to calculate the value of Avogadro's constant. Oh, okay, that's clever, isn't it? But the great thing is, because we know Avogadro's constant, we know what number we're looking for. Yeah, so hang on a sec. We have 1 gram, 1.0078 grams of H1 atoms. Okay, we know that and that's given me, that's 1 mole. Yeah, there's 1 mole. Well, we know that 1 mole equals Avogadro's constant. We know that that equals it. Well, so if that's the grams, and then we also therefore know the mass of a single atom. So this is 1 mole of atoms, and versus 1.6734 times 10 to the minus 24 is for a single atom, for 1 atom. Well, hang on a minute. Divide the bigger by the smaller. 1.0078 divided by, so this is 1 mole of atoms, and this is 1 mass of atoms. That's 1 atom. So we need to work out the number of atoms. So just divide the big number by the really, really tiny one. 1.6734 to the power of, there you go, Emmeline, minus 24. And I get Avogadro's constant. So my final bit of maths, yeah, this is 1 atom, and this is lots of atoms. Yeah, lots. So I'm going to divide those two numbers. Yeah, and so if I do 1.0078 divided by the mass of a single atom, I'm going to get the number of total atoms in the system, 10 to the minus 24, and I get 6.02. It is the exact number we'd usually give, which is very interesting, times 10 to the 23. Give it to 5 sig fig. Ooh, I've just dropped the mark. That's how they're getting around people knowing the number. So I've got 6.0225 is my answer, times 10 to the 23. There we go. And that is 5 sig fig. I like it. Okay, how does the number of atoms in 1 mole of argon compare with the number of molecules in 1 mole of ammonia? Same. That's amazing. Yeah, because if we've got 1 mole of atoms, of argon atoms, yeah, 1 mole of atoms, and 1 mole of molecules, yeah, NH3, yeah, 1 mole of molecules, then they're the same. They're equal. Yeah, if it said the atoms in ammonia, then that would have been 4 times larger. Yeah, but it's not. It was molecules, so they're the same. I like it. That brings us to the end of the homework. Wow, guys, I feel like you have just for the first time had a real taste of what A-level looks like. Let's look at the total marks. 1 mark there, 2 marks there, 1 mark here, 1 mark here, 4 marks here. Calculate the mass in grams of a single isotope. 1 mark there, 1 mark there, 1 mark there, and 2 here and 1 here. Total marks, let's add them up. Yeah, zoom right out. So 1, 3, 4, 5, 9, 10, 11, 12, 13, 14, 15, and the total is out of 15. Now that was a really, really much more challenging homework. That, guys, really does show you how hard this gets. We're going to have, now, I'm having done this for such a long time, I know that there, much harder. What that means is I'm going to get a much bigger spread of data. Yeah, I'm going to have, rather than everyone being lumped together at the high end, I'm very aware that that now is going to give us a much more varied result. It's going to be very interesting to see your data. So onto the sheet, you guys are all there. It's nice to see. Aisha still hasn't filled in her last one for Avogadro. God, I'm really sorry. I gave you a homework much harder than the previous one, rather than a reinforcement, really. That's really hard. So this was Avo 2. Avogadros 2. Much harder, out of 15. I'm really sorry for that. Yeah, unfortunately, that is actually the level that you guys have got to get to. So you can fill in your data now, folks. Oh, this laptop's rubbish. Sometimes it just really does do my head in. There we go. You guys can now fill in your data. It'll be interesting to see how you guys have got on. Very challenging. Much harder. Even had a reacting mass really in there that you guys haven't seen before. No Angel this morning. No Angel. We've got 20 minutes to do PV equals nRT. Amazing. I don't want to rush you guys. That was a hard homework, that. And I am very aware of it. Don't want to rush you. There we go. Don't want to rush you guys. Right. So today's lesson is moles and gases. There we go. Okay, so my learning objectives I added onto the YouTube video. Number one is I need you guys to know your equation, and they're not going to give it to you, folks. PervNert. PV equals nRT. PervNert. I teach pervert because it's easy to remember. Yeah. So PV equals nRT. I need you then to understand the units. Understand the units of each part in the equation, of each symbol in the equation. I don't like symbol. Understand the units of each. I'm just going to leave it at that. That works. Next, I then need you guys to be able to know your standard conditions. Yeah, standard conditions. And I also need you guys to be able to then access exam questions on gases. To be fair, I probably won't get to that today. Okay, I'm curious to see how people are getting on. No one's inserted any data yet. That's odd. It's not like you guys. I don't know why. Oh, I feel like I've lost you guys. Okay, I'll continue. It'd be nice to see results going in, guys. If you could put them in, I'd really appreciate that. Okay, so you guys knew from GCSE. At GCSE, moles and gases was really easy. Yeah, so at GCSE, you guys had a lovely, easy equation. Yeah, GCSE gas moles. Gas moles. You guys had the equation, number of moles is V over 24. Now that was assuming your volume was in dm cubed. Yeah. You also had another version of it. Number of moles is V over 24,000 if you were in centimeters cubed, cm cubed. Yeah. Well, at this point, we realize that this really just is not okay. I actually hate Edexcel for using this at all. It used to be an A-level as well, and it used to drive me bonkers. Yeah, the reason being is we know that gases are affected by temperatures massively. Yeah, so what we now need to call this is we now evolve this into what is called the ideal gas equation. Now, I need to explain to you guys really quickly what ideal means. Yeah, now this is where I have to do a little bit of derivation, but the reason why we know that gases, ideal gases. So let's do facts. Number one, gases are affected by temperature and pressure. it will change their volumes. So what we now need to do is we need to just look at each one of these. Yeah. So if we look at temperature, yeah. So if we take the volume of a gas, and we can do this in dm cubed if you like. Volume of gas, I'll put my units as dm. Yeah. And then we look at temperature. What we realize is that the graph is a straight line. Now, this is the reason why you have what's called the ideal gas. Now, the reason for this is because you'll notice that the graph doesn't start at 0. Yeah, there's a really odd piece here. It is a straight line, which means that we can just say that temperature is going to affect the number of moles directly, as long as we are in what is called the ideal range. This is the ideal range. Yeah. And you'll probably recognize this. The graph then suddenly would drop off. Yeah. If you leave the ideal range, when you get down to low temperatures, all of a sudden the graph drops off. And there is an explanation as to why. We've changed state. Yeah. Change of state. Which means it's no longer a gas. We're going to now have gone from gas to liquid. Yeah, that's what we've now done at this point. Which means at temperatures below or close to, you always tend to say, by the way, that the ideal range is above. This is the ideal range, really. You want to be nowhere near the change in state temperature, nowhere near its boiling point. If you're anywhere near it, it's going to start to behave like a fluid, and you're then going to lose your volume. It'll rapidly start to change. So we've got to make sure that we are above, way above the boiling point. Yeah, ideal range above boiling point. Now I'm actually saying well above. Yeah, people often then say, well, how far above do you need it to be? It's a tricky question, that one. Yeah, above boiling point. Way above. You want to be as high as possible, really. So that's why it's called the ideal gas. Yeah. So what does it look like? I'm suddenly realizing I've got there were some quite funky animations for this. Oh, they're really good scores. I'm really happy with those. Really good scores. Well done, guys. That's great. Wow. Really good. Just want to quickly show you some things. This is Boyle's law. I want to try and do animation. Let's see if I can do this. I'm suddenly realizing I'm going to run out of time on this lesson. Well, I can do a second one. Boyle's law. I didn't really want to do a YouTube video in a YouTube video. It might be an easier GIF or something. Images. Pressure and volume. Yeah. And then temperature. We'll do Charles's law as well. So this is the pressure one. So what's going to happen to the volume of gas as the pressure increases? Right, you can see the fact that you get this rather lovely curve. Yeah. Now, the reason for that, now this is often, people often ask me what the purpose of R is, the ideal gas constant. Well, the ideal gas constant takes into account this curve on the pressure. So the one for pressure, volume and pressure, yeah, of course, is like this. But what this means is because we realize that these factors are affecting it, we now have to include these in our equation. We need to include pressure and temperature. So we now get the ideal gas equation, and I'll do this in big. Yeah, I'm going to do it in blue. Yeah, PV equals nRT. So the P, of course, stands for pressure. P stands for pressure. So if I'm going to calculate the number of moles in a gas, I'm going to need the pressure of that gas. I'm going to need to know the volume. Now, this, of course, is what we've been using with V over 24, making massive assumptions about pressure and temperature, which I'll come to in a second. And, of course, we all know as moles. R is the ideal gas constant. Ideal gas constant. And you need to know a value for this, which is 8.31. I actually learned 8.314 for mine. I'll talk to you about units in a minute. Yeah, And then temperature, of course, over here, temp. So just quickly now that we've picked up what each part of the equation is, I'm just now going to quickly mention how did we ever manage to get to V over 24? Yeah, V over 24. The reason why you do this is we make a massive assumption. This equation only works, this equation only works if we assume standard temperature and pressure. Now it's actually given a symbol standard temperature and pressure. Standard temperature and pressure is given the symbol, this one. It's like a train station symbol, like that. It's a circle with a line through it. Is the ideal gas constant the same for all gases? Yes, it is, Oliver. Absolutely. But now you guys learned at GCSE that all gases, no matter what they are, occupy the same volume with the same number of moles. So 1 mole of any gas occupies the same amount of space. Yet the particle size doesn't actually matter. As long as you're way above its boiling point, they will all have the same volume. Yeah, which is 24 dm cubed for 1 mole. Yeah. So standard temperature and pressure. Now we need to actually define what that is. So they decided to come up with a standard temperature. The standard temperature is 25 degrees Celsius. Now, here's the next bit. Guys, I've now got to teach you temperatures because you can no longer use Celsius. Celsius is dead. Yeah? What we now need to do is translate to a new unit of K, which is Kelvin. Now, just to explain why, is because temperature is a measure of vibration of the particles, and you can't get negative vibration, so Celsius is not appropriate. So Kelvin came up with a unit that starts off at absolute 0. So 25 degrees Celsius in Kelvin is 298 Kelvin. Now, what that means is, what they have added, and you've got to learn this is important, nota bene, yeah? To convert from degrees Celsius to Kelvin, yeah, going in this direction, you add 273. Yeah? If you want to go from Kelvin to Celsius, yeah, you're going to take away 273. Does that make sense? You can't get negative Kelvin. Yeah, I'm now just going to quickly mention an example, e.g., 0 Kelvin. 0 Kelvin is called absolute 0. Absolute 0. Nothing can go lower. And that temperature in Celsius, minus 273.14, if you really want to push me that far, 273 degrees Celsius. You don't need to know the 14, but I do just because I'm nerdy. So it's quite nice to do these, and you guys have to use Kelvin now because Kelvin is a true measure of vibration. You can't have negative vibration, so Celsius is not appropriate for this. Pressure is 100 kilopascals. So, I shouldn't do that. I should actually do 100,000 pascals. Yeah, and yes, units. Are we allowed to use 273 or do we have to use 273.15? It's not 15, it's 14. Is it 15? I might be wrong there. Someone check me on that one. No, you need to use 273, Oliver. Keep it easy. Yeah. So pressure is measured in pascals. Now you're going to come across a whole load of different units for pressure, which is a bit of a nightmare. But you guys need to know that these here are the standard conditions. You have to know them. It's part and parcel available. 298 Kelvin, standard. 100,000 pascals, standard. You guys need to know those. It's really important. Add that to your notes. Standard temperature and pressure, 100,000 pascals and 298 Kelvin. Right. So that's how you manage to get around PV equals nRT at GCSE. We just assume everything is under STP. I'm just going to quickly write that down. Yeah, these here account for what is called STP, standard temperature and pressure. Yeah, standard temp and pressure. That's how they get around it. STP. You're going to come across STP a lot. Okay, so I now need to do, the rest of it is relatively straightforward. All we need to know is to use this equation. And this is where my lesson is going to pretty much come to an end. But because I've only got 5 minutes left. So here's the thing. And these are more nota benes. Going to do this one in red. Yeah, nota bene. Make that a bit thicker. I didn't actually want to do that. Oh, wow. I've zoomed right in. Okay. I've gone and made a schoolboy error there. Yeah, okay. To use this equation, yeah, to use pervnerd, to use this equation, PV equals nRT, to use PV equals nRT, you must have ... This is a nota bene. Yeah. Number one, temp must be temp in Kelvin. Yeah, must be in Kelvin. Number two, pressure must be in pascals. PA. I'll just put PA. Yeah, and then I'll put in brackets pascals. Must be in pascals. What that means is the pascals is going to be big. Yeah, that's important. So that there is super important because what they're going to get you to do is they're going to constantly be asking you to do conversions. Yeah, moving from Celsius to Kelvin and kilopascals to pascals. Just to quickly do some of those as an example. Yeah, conversions. I'll go back to black. Conversions. Common conversions. Yeah, if I've got 173 degrees Celsius, convert to Kelvin. Yeah, so all you do is, Celsius to Kelvin, add 273. That's not complicated. We like this game. Yeah, Celsius to Kelvin, add 273. Yeah, so 173 plus 273, I get 446. 446, not complicated. Yeah, very common conversion. Next one, convert 160 kilopascals, convert to pascals. Well, that's not complicated either, times by 1,000. Yeah, we know that kilopascals are bigger units, so we need to go to the smaller ones, which means there's going to be more of them. So we're going to have 160,000 pascals. This is not complicated. I am going to mention one other unit for pressure. Yeah, so one other unit for pressure is atmospheres. Yeah, now you guys don't really need to use this particularly much. They'll tend to always give it to you in kilopascals or pascals, but you will see questions with atmospheres in it. So you guys, all you need to know is that one atmosphere, now this is where I've got to be careful. One atmosphere, according to Edexcel, is 100,000 pascals. This is not true. Yeah, this is a lie. Yeah, lie from Edexcel. Yeah, one atmosphere is actually equal to 101,342, 324. Oh, I'm going to lose my number. 324 pascals. I think that's right. Somebody Google me. Somebody check me. It's really close. It's going to be really close. I've got the first four numbers right. It's whether or not I've got the 2, 4 the right way around. So what that means is you should never use atmospheres because this is the true value. You should never really use it because it's a bizarre number. Yeah, we don't like it. They'll always give you the conversion, the method of conversion if you need to use it. So try not to worry too much. 2.5? No! Oh, can you believe it? Do you know what? I'm giving myself that. I mean, I had it to what? I had it to 6 decimal places, 6 sig fig. You are one off, Mr. Duncan. Oh, so close. That's really upsetting. I tend to do 3, 2, 4, 3, 2, 5. Oh, so frustrating. Anyway, so at this point, now that we've got that, guys, we're actually at the end of the lesson. If I quickly go back to my learning objectives, number 1, all of you guys will have to learn your equation. Know your units for each part of it. We've now done it. We've got the standard conditions. We've got them. We just now need to do our exam questions. So just before you go, I know I've got literally 60 seconds left. What I want to quickly do is to show you an ideal gas question. So it shouldn't take me shouldn't be very hard for me to find here. I don't think. We will see. Year A-level papers, AS paper, paper 1. Let's just go for that one. Let's have a quick look. And there's always an ideal gas. The problem is that Edexcel sometimes, what paper is this? 2018. Where is it? Where are you? Oh, I've just found another Avogadro's constant one. Yeah, moles in solution. Oh, there's another one. Oh, 2018. Darn it. Let's see if we can find an ideal gas equation. Where are you, ideal gas? Do you know what? I shouldn't really be looking at this. I know a better place to find it. My booklets. Documents. Backup files. Just before you go. If you need to go, you can go. Yeah, but I'd like to think that you'd want to hang around. Booklets. Let's go for AQA because I know those a little bit better in terms of finding them. Calculations, amount of substance. Right. Question database. AS module 1, calc book 2. Right, let's find it. And there it is. So I'm just going to quickly snip this, guys, and put it into my lesson. New. Oh, we're going to need the whole question. Because it's part B. Oh, no. That's a bit irritating. Do I need it? No, maybe I don't. Okay, no, I don't. I can snip this directly. Excellent. Let's just quickly grab that. 4 marks as well. So edit, copy, paste that into my lesson. Here's your first exam style question. It's not a complicated one. This great thing is PV equals nRT is actually quite nice. Oh no, we couldn't post it from the clipboard. Oh, you mean thing. Why not? Why? Okay, I'm just going to do full screen snip. It's on the YouTube video anyway. Go, come on. Do what I'm asking you to do. Right. Okay, guys. A second sample of nitroglycerin was placed in a strong sealed container and detonated. The volume of the container. Oh, I've forgotten one. Thank you. This is why you've got to do exam questions. Guys, sorry. We've missed one more thing. I've forgotten one more thing, haven't I? Add this to your notes, please. Number 3. Volume. So easily done. Yeah, volume. 3 is volume. So volume now becomes a bit of a nightmare. Volume must be in meters cubed. What a nightmare. So you've never come across meters cubed before. 1 meter cubed of gas, yeah, is equal to 1,000 decimeters cubed of gas, which is also equal to 1 million centimeters cubed of gas. Isn't that cool? And you have to input in this. So if I go back to that question, now I can answer it. So first of all, state the equation. PV equals nRT. What a nice 1 marker that is. Boom. Yeah. Next, right, we're calculating pressure. Reorganize for pressure. So there's going to be a mark for going, bring the V down. Yeah. So I'm not going to do that up there because I've got to do that one. So I'm going to go pressure equals nRT over V. Right, insert all my numbers. Right, I've got moles. There's moles. P equals 0.873 of gaseous products, fine, times by 8.31, which they've given you, times by the temperature, which is in Kelvin. Don't need to do any conversion. How nice is that? All over, and it's given me the volume in meters cubed, which is amazing. So I can just now run that through, no conversion needed. 0.873 times by 8.31 times by 1,100, divide that by 1 exponential minus 3, sorry, Emmeline, and I get a massive pressure. I get a pressure of 7980093 pascals. It will spit out in pascals. If you want it in kilopascals, divide it by 1,000 and you're done. That's the end of the lesson today, guys. I really did need to finish that. I will set you guys a homework on using PervNet on the classroom. Guys, have a great rest of your day. I'll see you all soon.